It begins with a fragment, a whisper from the deep past, preserved in stone. Imagine a windswept quarry in Scotland, the air crisp and cool. A geologist chipping away at a slab of ancient sandstone suddenly stops. There, imprinted in the rock, is something quite extraordinary. It is not the familiar shape of a shell, nor the delicate tracery of a fern. It is a trackway, a series of small, yet distinct footprints, left by something that scuttled across a muddy shore some 428 million years ago. This was a world utterly alien to our own, a time before the first dinosaurs, before the great forests, before even the first fish had dared to crawl from the sea. These faint impressions in the stone represent a monumental moment in the history of life. They are the oldest known evidence of an animal walking on land. The creature that made them was a pioneer, a tiny explorer in a vast and empty world. It was likely a myriapod, an early relative of today's millipedes, and it was an arthropod. Insects, spiders, crustaceans, poised to inherit the earth. Let us travel back further still, to a time around 600 million years ago. The world is almost unrecognizable. The continents we know today are smashed together into a single colossal landmass. Geologists have given it a name, Panacea. It is a stark and barren supercontinent, a vast expanse of rust-colored rock under a pale alien sky. There are no forests, no grasslands, no soil to speak of. The land is a desert, scoured by relentless winds, baked by a sun whose rays are unfiltered and ferocious. This is an Earth without its shield, a world without an ozone layer to protect it from the sun's deadly ultraviolet radiation. The atmosphere itself is a strange and hostile cocktail of gases. There is very little free oxygen, the gas that gives us life. Nitrogen, carbon dioxide, methane. The sun beats down with a harsh, unfiltered glare, its UV radiation sterilizing the surface of the land. Nothing, it seems, could survive here. Any life that dared to venture from the safety of the water would be scorched in an instant. The land is a realm of death. This early Earth spins faster than it does today, making the days shorter. The moon is closer, looming larger in the sky and exerting a much stronger gravitational pull. This creates colossal tides that sweep across the shallow seas, churning the waters and eroding the barren coastlines. The planet's climate is in a state of extreme flux, swinging between intense greenhouse heat and catastrophic global ice ages, known as snowball Earth events, where ice sheets may have stretched from the poles all the way to the equator. It's a world of violent contrasts, a planetary crucible where the conditions for life are only just beginning to form in the most sheltered of places. And yet, in the heart of this inhospitable world, something miraculous is happening. While the land remains dead and empty, the oceans are stirring. For billions of years, life remained a simple, microscopic affair, hidden away in the global ocean. But around 2.4 billion years ago, a new kind of organism evolved, and it would change everything. These were the cyanobacteria, also known as blue-green algae. They performed a trick that seems simple to us now, but was revolutionary at the time. They learned to harness the power of the sun. Through photosynthesis, they could take sunlight, water, carbon dioxide, and convert them into energy. And as a byproduct of this miraculous process, they released a waste gas. That gas was oxygen. At first it was a poison, toxic to most other forms of life. This great oxidation event was perhaps the most significant pollution event in Earth's history. The oxygen released by these tiny algae began to build up in the oceans. It immediately reacted with dissolved iron, causing it to rust and settle on the seafloor. For millions of years, the oceans literally rusted, creating the vast banded iron formations that we mine for steel today. Only when the free iron in the oceans was all used up could oxygen finally begin to seep out of the water and accumulate in the atmosphere. This process was incredibly slow, taking hundreds of millions of years, a gradual terraforming of our own planet by its smallest inhabitants. The slow rise of oxygen had a profound effect. It was a crisis for the anaerobic life that had dominated the planet for eons, but it was an opportunity for others. Then, around 541 million years ago, something extraordinary happened. In a geological blink of an eye, the oceans erupted with a dazzling diversity of complex animal life. This event is so sudden in the fossil record that we call it the Cambrian explosion. For the first time, we see creatures with shells, with legs, with eyes, and jaws. The blueprints for nearly all modern animal body plans were laid down. The seas, once dominated by simple, soft-bodied organisms, were now teeming with a bizarre menagerie of new animals, all competing, hunting, and surviving. Among the most successful were the trilobites. They were arthropods, distant relatives of today's insects and crustaceans. They came in thousands of different species, ranging from the size of a fingernail to the size of a dinner plate. They had hard, segmented exoskeletons for protection and complex compound eyes, some of the very first eyes to ever see the world. They scuttled along the seabed, feeding on organic debris, becoming the ubiquitous grazers of this new underwater world. But where there is prey, predators will surely follow. The Cambrian seas had a truly terrifying top predator. Its name is Anomalocaris, abnormal shrimp, unlike anything that had come before. At up to a meter in length, it was a giant for its time. It had 2 large stalked eyes, a circular mouth filled with razor-sharp teeth, and 2 formidable grasping appendages at the front of its body, which it used to snatch unsuspecting trilobites from the seafloor. It was the world's first super predator, the ancient equivalent of a great white shark, and its presence drove the evolution of defensive armor, like the hard shells of the trilobites. This was the birth of the modern ecosystem. For millions of years, the land remained a forbidden zone. The sun's ultraviolet radiation was simply too intense for unprotected life to survive. Cyanobacteria had been pumping oxygen into the air for eons. Oxygen molecules, O2, were abundant. Bombarded by UV, O2 atoms were being rearranged into ozone, O3. A thin layer of ozone slowly accumulated high in the atmosphere. That layer acted like a planetary sunblock, absorbing the worst UV and making the surface safe. The ozone shield was a turning point. With it, the Great Migration could begin. The first pioneers were plants, not animals, related to modern mosses, related to liverworts, clinging to damp river and pond edges. These plants began creating the first soils by breaking down rock. They greened the edges of continents and created habitats. They provided food and shelter for future land animals. And follow they did. Ancient Scottish footprints show the first animal steps, likely a small millipede-like arthropod around 428 million years ago. Maybe it left water seeking food among new plants, or escaping crowded, dangerous seas full of predators like the eurypterids, the sea scorpions, some of enormous size. Whatever the reason, it was a momentous step onto land. Arthropods were pre-adapted for land. Their exoskeletons supported them against gravity and helped prevent drying out. Their jointed legs were ideal for walking on solid ground. This began a new dynasty. While lobe-finned fish explored shallows, arthropods colonized the land. They diversified rapidly. The first insects, spiders, scorpions. For tens of millions of years, they ruled the new green earth. A kingdom headed into a golden age, an age of giants. We now arrive in the Carboniferous Period, which began around 359 million years ago. The name means coal-bearing, and for good reason. This was an age of vast, swampy jungles that stretched across the continents. The climate was warm and humid, and the air was thick with moisture. But these were not forests as we would recognize them. There were no flowers, no fruits, no birdsong. Instead, the landscape was dominated by colossal, primitive trees. Club mosses like lepidodendron grew over 100 feet tall, their trunks covered in a diamond-like pattern of leaf scars. Giant horsetails, tree ferns formed a dense, lush understory, creating a world of perpetual twilight at the forest floor. This was a world of breathtaking scale. The sheer productivity of these forests was immense. When these giant trees died, they fell into the stagnant, oxygen-poor water of the swamps. Bacteria, fungi that normally cause decay, had not yet evolved the ability to efficiently break down the tough lignin and cellulose of their wood. So, instead of rotting away, the dead trees simply piled up, layer upon layer, over millions of years. Under immense pressure and heat, this accumulated plant matter was slowly cooked into the vast coal seams that would one day power our own industrial revolution. We are, in a very real sense, burning the fossilized remains of these ancient forests today. And in these primeval jungles lived the true rulers of the Carboniferous world, the arthropods. They grew to sizes that seem the stuff of fantasy today. Imagine a millipede-like creature, Arthropleura, stretching up to 8 feet long, the size of a small horse, scuttling through the fern-choked undergrowth. It was the largest land invertebrate of all time, a gentle giant feeding on decaying plant matter. In the air, the skies were patrolled by dragonflies of the genus Meganeura, with wingspans of up to 2.5 feet, as large as a modern-day seagull. They were fearsome predators, their huge eyes scanning for smaller insects to snatch from the air. This was the undisputed peak of the arthropod empire. Giant scorpions, spider-like creatures roamed the forest floor. Cockroaches grew to several inches in length. For nearly 60 million years, these magnificent giants dominated the planet's terrestrial ecosystems. Our own vertebrate ancestors were there too, small, lizard-like amphibians, but they were minor players, scurrying in the shadows of the immense trees and the even more immense insects. So, we must ask the question, why did these arthropods grow so enormous? Why don't we see dragonflies the size of eagles? Why don't we see millipedes the size of cars today? The answer lies not in the creatures themselves, but in the very air they breathed. The vast Carboniferous forests were pumping colossal amounts of oxygen through intense photosynthesis. And because so much dead plant matter was being buried without decaying, the oxygen wasn't being used up. As a result, atmospheric oxygen levels soared to as high as 35%, compared to 21% today. Unlike vertebrates, which have efficient lungs to move oxygen in blood, insects and arthropods rely on a much simpler system. They breathe through networks of tiny tubes called tracheae, from spiracles directly to tissues. That system works well over short distances, but becomes inefficient as size increases. Oxygen can't diffuse far enough into inner tissues in large bodies. In the high oxygen Carboniferous, that limit was removed. With 35% oxygen, the concentration gradient was much steeper. Oxygen could penetrate much deeper through the tracheal system. This supercharged atmosphere broke the glass ceiling on size. It allowed giants like Meganeura. It allowed giants like Arthropleura. As the Carboniferous ended, the climate changed and the swamp forests died back. Oxygen levels fell toward modern levels. The tracheal system became limiting again. The giant arthropods could no longer get enough oxygen to survive. Their reign was over because the air could no longer support their size. It's a reminder of how deeply life is connected to planetary chemistry. The end of the arthropod empire and the end of the Paleozoic era came with a cataclysm of unimaginable scale. Around 252 million years ago, at the close of the Permian, the planet suffered its most severe extinction. The Permian Triassic extinction, the Great Dying. It nearly wiped out life on Earth. Over 90% of marine species vanished. 70% of terrestrial vertebrates disappeared. The world's ecosystems collapsed. The primary cause: colossal volcanic eruptions in what's now Siberia. Massive fissures poured out lava for over 1 million years. Flood basalts covered an area larger than Western Europe. The eruptions released immense carbon dioxide. They also released vast methane. Runaway global warming followed. Temperatures soared on land and in the oceans. Volcanic gases also sent sulfur dioxide into the sky. That mixed with water to produce acid rain. The rain poisoned soils. It acidified lakes and rivers. It devastated forests worldwide. As plants died, ecosystems collapsed. On land, the great arthropods suffered. Early amphibians starved. Reptiles also faced mass mortality. In the oceans, warming cut dissolved oxygen, creating anoxic dead zones. Acidifying seawater made life harder for corals. Shelled organisms couldn't build skeletons. Marine ecosystems crumbled from the bottom up. For giant arthropods, this was a perfect storm. Forest collapse removed habitat and food. The most direct blow: atmospheric oxygen dropped dramatically, from a Carboniferous high of 35% down to as low as 12%. Giant insects lost their oxygen-rich air. Myriapods likewise suffocated. Their respiratory systems failed. The age of giant bugs, nearly 100 million years, choked to an end. The world fell silent. Out of the ash and silence of the Great Dying, life, as it always does, endured. The extinction was a profound reset button for the planet, but it was not a complete wipeout. In the shadow of the fallen giants, small, hardy survivors clung to existence. Among the arthropods, cockroaches, beetles, ancestors of modern dragonflies. They were no longer giants, but they were resilient. They would go on to become the most diverse and numerous group of animals on the planet. A quiet success story that continues to this day. But they would never again rule the world as they once had. The extinction created a power vacuum. The ecological niches once occupied by giant arthropods and early amphibians were now empty. This presented a huge opportunity for another group of survivors, the reptiles. They had several key advantages in this new, hotter, and drier world. scaly skin that prevented water loss, amniotic eggs that could be laid on land, away from water, freeing them from the swamps. One particular group, the archosaurs, proved especially successful, ancestors of crocodiles, birds, dinosaurs. In the early Triassic, the world was harsh and simplified. As life recovered, archosaurs began to diversify and grow. They were evolving into the new dominant land animals. The stage was being set for the Mesozoic era, the age of reptiles. Dinosaurs rose to become the new giants. Their reign would last for over 150 million years, a dynasty built upon the ruins of a forgotten empire.